Hello and welcome to another Zozin session. How about that? So today we continue developing our programming language in Python, which is called Porth. You can find the source code of this thing in the description, right? And we've been developing this thing for quite some time already, so we accumulated like a playlist of the episodes of the development of this entire thing, and you can also find this playlist in the description too. So we already added quite a few features to the language, and I think the time has come to refactor the code a little bit, right? Because we were just piling the features on top without any consideration, right? And we have a bunch of concepts that were introduced at the beginning of the development, but now, as the requirements for the language have changed, they don't really make much sense. So it would be better to restructure things a little bit and refactor stuff. So I primarily work with statically typed languages like C, C++, Haskell, and like something that has a static typing. And Python for me is a rather unfamiliar language because it's a dynamic language. And I don't really know how people develop in dynamic languages, to be fair. But one way I refactor things in statically typed languages, I follow a thing that I personally call a compiler-assisted refactoring. Meaning that if I want to change a signature or a definition of a structure, I just go ahead and change it, and that breaks the code in a bunch of places that call that function or use that structure, and then I sequentially go through all of the compilation errors and fix them, effectively refactoring the whole code base, right? So I'm using the compiler to sort of guide me through the process of refactoring. Unfortunately, in dynamically typed languages, it's kind of difficult to do that. You can still do that, especially in Python, because Python, even though it's dynamically typed, it's strongly typed, right? It doesn't coerce types around, so if you change something, it will fail properly, but just in runtime. But that means you have to have a complete suite of tests that test all of the possible execution paths, which sometimes not always feasible, right? In statically typed languages, you just get that for free, essentially. But here's an interesting thing. In Python 3, there is an optional static typing. Did you know that? Yeah, there is optional static typing. Actually, it's not really static typing, it's just like optional typing. Let's take a look at this entire thing. So I'm going to go to the project and I'm going to create some sort of a file. So Python file, Emacs. All right, so let's actually do the shebang thingy. For some reason, why is so okay? So something is broken in my Emacs. I need to restart it. I really apologize for that. You know, the usual Emacs situation. All right, so everything seems to be okay. Let's do shebang. User bin environment Python 3, and let's assume that we want to define some sort of a function. I don't know what exactly is going to be called. Let's call it count lines, right? And this function accepts the file path, right? And it will return how many lines there is in a particular file, right? We want to open that file for reading, right? And I suppose we want to do the with block. And then I'm going to read all of the lines from this entire thing, and I'm going to simply return the length of this entire stuff, right? So, and what we can do, we can actually count lines within our current file. I guess we can do something like this, right? And then if I make this entire thing executable and do full pi, it didn't work. I wonder why. Because it's a file path, I'm really sorry. There we go. So I suppose I also need to print this entire thing. There we go. So we have 7 lines, and as you can see, it is correct. There is only 7 lines in this specific file. Right, so what you can do is you can annotate the types. You can say that the file path has to be a string, and count line returns an integer, right? You can do that, and this entire script is still going to work, right? So, but here's the problem. it's not checking these type annotations. I can say that it returns a string and it will still work without complaining anything. So this kind of like a type annotations is essentially just a documentation feature, right? It's a syntactical documentation. But here's an interesting thing. As far as I know, all of these type annotations, even though they're ignored by the interpreter, primarily, they're still available through reflection of the language. So you can write a third-party tool that takes all these annotations and just does something with them. For instance, type check. And as a matter of fact, people have developed tools like that, and one of such tools is called MyPI. That's right. So optional static typing for Python. So essentially what it does, it looks for these type annotations and tries to perform the missing static analysis step for the Python, right? And for instance, we can just give it a try. So what if I do MyPI foo pi? Will it complain? Okay, incompatible return type value got int expected string, and it complains exactly where we introduced an error, right? So len returns an integer, but we said that count line is supposed to return string, which is not correct. So, and we didn't even execute the script, by the way. So that error was caught in a compilation step. There is no compilation step, like a type checking step. So if we change it back, this thing will work. So we have some sort of static typing. So through my experience, MyPI is okay, but sometimes it doesn't work correctly. Sometimes it simply doesn't check the things that it's supposed to check, but at least it's something, right? At least it's something. I'm not a big fan of dynamic languages, but if you're stuck with Python, MyPI is a good thing to have, right? It's not ideal. It's not as good as static typing, for instance, in, I don't know, Rust, for instance, or Haskell, or strong statically typed languages. It's not as good as that. But if you have no choice, at least it's something, right? It's like a TypeScript for JavaScript, right? It's not ideal, but it's something. And recently I actually started to use type annotations in the implementation of my language, and they're great, right? So MyPI actually caught a couple of mistakes in here that I didn't notice. So as you can see, I'm annotating. So here's the function. It accepts a program, it accepts a string, doesn't return anything, and yeah. So I'm also running MyPI in CI, in continuous integration, and yeah, the experience primarily pleasant. And what I want you to do in this video, I want you to see if this optional static typing is going to help me to refactor the code the same way static typing helps me to do that in languages like C++, C, Haskell, and so on and so forth. You know, the real programming languages. I mean, the statically typed programming languages. Right, so that's precisely what I wanted to do. So let me quickly grab a cup of water, and we're gonna take a look at what we need to refactor and try to see if MyPI will help us. So, all right, let's continue. So in our language, we have a notion of an operation, so-called OP, right? So let's take a look at this entire thing. Class OP. There we go. Here is a single operation. Back in the early days of the development, like a week ago, right? Or maybe 2 weeks ago, I don't remember. One token of the language, rather word of the language, corresponded to a single operation, right? If we take a look at how the language looks like, so let's take a look at a very simple example. So foo Porth, right, and there we go, and something like 10, 20 plus print, and as you can see, we have 4 words in here. Well, Emacs says 3, but this is because it doesn't consider plus a separate word, but our language does consider plus a separate word. We have have 4 words, and each individual word is a single operation. So there was a one-to-one correspondence to between tokens and words. And by the way, this is a valid program. So this Porth is a stack-based language, meaning that each operation sort of manipulates the stack. So the operation 10 pushes number 10 to the stack, 20 pushes another number to the stack, plus takes 2 elements at the top of the stack, sum them up and put them back. Print extracts the top element on the stack and prints it. Right. So essentially what this thing will do, it will sum up 10 and 20 and print 30. Right. And we can even check how it works. So we can do Porth and we can simulate. Right. So we can basically interpret this entire thing, and it's supposed to be 30. As you can see, it is 30. So what's cool is that you can actually compile this entire thing into assembly, right? So as you can see, if I use a different subcommand, it generates an assembly file, then compiles that assembly file with a NASM, and then links it into a final native executable. Right, so the assembly that we get compiled looks like this. It's a pretty simple, straightforward assembly, and here is the executable file, right? So as you can see, it's a LF64-bit executable, and it's statically linked, right? And as you can see, it does not depend on anything. Here is the output of LDD, and if you try to execute this entire thing, it prints 30 as well. So as you can see, it's a native language. Even though it's written in Python, in interpreted language, it's still, compiled static language. All right. So, but recently we introduced a thing called macros. So, and essentially what macros allow you to do, they allow you to take a sequence of tokens, right, and hide them behind a single token. For instance, we can create a macro. As you can see, it highlights the keyword. So I recently implemented very quickly the editor mode, the support for Porth in Emacs. So it is located in the editor folder, right? So the entire source code is actually open. You can find the source code in the description, and the folder editor actually contains the mode for Emacs. So now I finally have a highlighting for my own programming language, which is kind of nice. All right, so what I can do here, I can say that I want to have a macro called numbers, and I'm going to put 10 and 20 behind this macro. Right, and there we go. And now, if I use numbers, the compiler will expand a single token into 2 tokens and only then compile them. As you can see, a single token does not correspond to a 1 operation, and now corresponds to 2 operations, or 3, or 4, and so on and so forth, to as many operations as you want, or maybe even infinite amount of operations, right? So right now, macros are pretty unsafe. If you write a recursive macro like this, it will go indefinitely. As far as I know, there is some sort of like a limit on the amount of tokens that you can have. We can try to compile this entire thing and see. There is no limit. Yeah, apparently I removed that limit somehow. So yeah, we're gonna develop some sort of like a safety mechanism for recursive macros in the next episode. Right, but anyway, so as you can see, a single token does not correspond to a single operation, so the one-to-one correspondence between operation and token is completely broken. And furthermore, the macro definition consists of the tokens themselves. And what's interesting is that this macro definition has like 8 tokens, right? It has 8 tokens, and none of these tokens correspond to any operation in the source code, meaning that it's just an instruction for the compiler, right? If you encounter this word, just replace it with this sequence of words, right? But these tokens themselves don't correspond to anything. They're going to be removed from the final program. And for instance, if you never use the numbers, this macro will never be expanded. This sequence of tokens will never appear. So the correspondence between a single operation and a single token completely broken, right? But we still use that correspondence within the source code because that's how it was designed from the beginning. And that creates a lot of weird problems. For instance, when you're trying to generate a code, right? So the compilation process just produces the sequence of operations, right? So the generation takes a program, and if you take a look at the program, at the definition of the program, it's just a list of operation, right? So program is simply a list of operations, right? And we take a list of operations and we iterate through a list of operations, and for each operation we generate an assembly code. And since there is one-to-one correspondence between operation and the token, there should be an operation for something like a macro, right? So it should be an operation that has to be compiled into something, but this entire thing should be eliminated, right? So, and if we take a look at what we do when the generator encounters a macro, it will fail, right? Saying that this thing should be unreachable. All of the macro definitions should have been eliminated at the compilation step, right? So compilation step should have just removed all of them, but if they reached this place, that means there's something wrong. The thing is, we shouldn't see this kind of stuff in the first place. The macro and also include, by the way, just includes files, so you can do things like include std Porth. Also, by itself, it doesn't introduce any operations, it just expands into the tokens inside of this file, so by itself it's also going to be eliminated. So these two things shouldn't be here in the first place, because they're not operations. They're more like a keywords. So, and that's precisely what I want you to do today. I want you to take operations and just split them into a bunch of separate entities, right? Because they want to be separate entities. They want to be keywords, they want to be built-in words, and so on and so forth, right? And I just want to see, will the static typing of Python help me to do that efficiently, right? Because refactoring a big code base in a dynamic language is always pain in the ass, right? Because if you miss something, the interpreter won't tell you anything unless you actually execute that place where you introduce an error. And our program is already almost like 1,000 lines of code. We lack like 48 lines to be 1,000. I wouldn't say it's a big program. For me, 1,000 lines of code is actually nothing, right? But maybe for new developers, 1,000 lines of code is actually a lot of code. I don't know. Though 1,000 lines of dynamic language code is actually quite scary, not gonna lie. But we have MyPI, so that should be fine. All right, let's go ahead and try to see what we can do in here. Cheers. This is just a water, by the way. Okay, so here we have operations, and operations are essentially bytecode of intermediate representation of the language. All of these things like plus, minus, multiply, diff, mod, and so on and so forth, they're more like built-in words. They could be implemented maybe in the language themselves, but they're sort of like internal built-in words. And this is something that I want you to separate. I want you to separate built-in operations from the rest of the kind of operations, I think. I think that's what I want to do. Or maybe that's not a particularly good idea. Maybe what I want to do, I want to actually introduce keywords, right? So let's go ahead and do that. We're going to have a class keyword type. Do I want to have a keyword type? I don't think so. Maybe it's going to be just called a keyword, and this is going to be an enumeration. And the kind of keywords we're going to have is if, and, else, while, do, macro, and include. What's interesting is about if, and, else, while, and do is that even though they're keywords, they're also operations. So I think there will be a little bit of a duplication between operations and keywords. Right. So I'm going to copy paste this entire thing in here. Right. So this is now a keyword, and we're removing macro from operations. Now this entire thing is a keyword. Okay. So, and keyword is sort of like a kind of token, right? And the token kinds we have in here is word, integer, string, character, and I think we need to introduce a keyword in here. Right, we need to introduce a keyword. And as we introduce a keyword, right, token is supposed to be, can be one of those. It could be integer, string. So integer is used for int and character. String is used for string and word. And for the keywords, I suppose we're going to be using a keyword. Right, by the way, union is one of the types, and essentially it's coming from the module typing. It's actually very cool to a module. Python typing. I wonder if I can quickly find it. Python typing. Just a second. Python typing. Right, so you can actually use more complicated types than string and integer. You can have like list, dictionaries, and also things like unions. And unions basically means one of those types, right? So response is either iterable, or integer, and so on and so forth. So you can have complex, invariants and stuff like that. So and this is precisely what we're doing. So for my case, token is basically a union, right? It's basically a union of, it's either integer, string, or a keyword. Okay, so I made a bunch of changes in here, right? I made a bunch of changes, and I wonder if that's enough for me to actually make MyPI complain, right? So right now, if I stash all of my changes, right? If I stash all my changes and I try to do MyPI on Porth, right? Let's take a look. So it shouldn't complain. Okay, so it says that everything is successful. But now, if I apply the changes that I made, right, hopefully something will break, right? Hopefully, we'll see. So MyPI, and okay, so it broke in a bunch of places, and specifically it broke where I would expect it to break. So since macro and include are not operations anymore, I need to remove this entire thing, right? So now it is not available in here. Okay, so we removing this entire thing. All right, so there's a couple of places. Oh, okay, so we have a dictionary correspondence between the name and a built-in word, and this one is interesting. So I want to separate built-in words from the keywords. So I'm thinking that maybe I'm going to remove not only macro and include, but also if and else, while, do, and macro. And I'm gonna have a separate table of keyword names or something, right? So keyword names, and let me see what we can have in here. So there is if. So if is keyword if, then we have and, keyword and, else, keyword else, then while, do, macro, and include. Okay, so that's cool and all. And let's go ahead. So here's an interesting thing. I usually like to assert the following things, right? So this code is written from the assumption that there is 6 keywords. If I ever add more keywords to the definition, I want this code to break and let me know that I need to add more things in here. So exhaustive keyword names definition. There we go. Okay, so let's try to recompile this entire thing. Include has no attribute include. Yeah, so I forgot to capitalize this entire thing. All right, so what do we have in here? Okay, so here we are in a function that compiles the program, right? Actually, it compiles the tokens, right? It takes a sequence of tokens and produces a sequence of operations. And that's what we need to do in here. This one is rather interesting. So what is it complaining about? Argument value has incompatible type. So, oh yeah, value is like it could be a keyword, right? It used to be only integer string, and now it's a keyword. I suppose. So here we are checking the keywords specifically, right? And the keywords actually produce some reasonable values. So as you can see, these are operations, but these things are not operations anymore. They became keywords. So I think the stuff we need to do in here is, right, so here's the token. If the token is a word, we're trying to do one thing. If the token is an integer, string, and character, we need to add a new thing in here. If token type is token type keyword, right? So this is going to be keyword. We have to do this thing, right? We have to move this entire code under that branch, right? We need to move everything under that branch, and it's going to be kind of difficult, not gonna lie. Because I don't see the edges of the blocks, so I have to sort of pad everything with spaces and whatnot. Yeah, in a C-like programming language, it will be easy to reformat everything. 1, 2, 3, 4. There we go. So now everything looks okay. So we know for a fact that token type is a keyword. And now what I need to do, I need to take a token. I actually need to replace OP type with a token value, I think. So let me actually select this entire thing. Oh boy. All right. So query replace token type, token OP type, token value, right? So this is a token value. There we go. And also it makes sense to replace OP type with keyword, right? OP type with a keyword. So that should be sufficient enough. That should be sufficient enough. And all of that is in dynamic language, by the way. So it is very, very scary for me to modify this entire thing. Okay, so OP type should be replaced with the keyword now. So I'm not going to modify this thing. So this is a keyword. Program type. This one is interesting. So I suppose we're going to keep it OP type, right? Because it's a program. And now keyword, keyword, keyword. There we go. Cool. So in the key word, we expect how many? 6 keywords, right? Then keyword, yeah, there's 6 of them. Exhaustive keywords handling in compile token to program function. So we're trying to handle this entire stuff pretty exhaustively. Okay, so let's see if MyPI will complain now. Okay, so it's complaining about some stuff. Okay, cool. So yeah, it still doesn't believe that token value could be an integer. I think what we need to do here is we need to assert that is instance, right? Token value is an integer, right? And if it's not an integer, it's probably a bug in the lexer. Lexer is supposed to produce the correct correspondence between the type and actual value. This could be a bug in the lexer, right? There we go. So is it going to still complain there? Okay, so it's a similar situation. So we probably need to check for str in here, right? Is that it? I think that is kind of it. Okay, that's cool. Yep, this is item none of optional OP has attribute type. This one is really interesting. First of all, I'm not sure that this is correct to even compare it like that, so it has to be OP type. So I made a mistake in here, that's for sure. But at the same time, why this thing is optional? Type is not really optional. I don't quite understand. Item none of optional OP has no attribute. Is that because stack pop in fact returns an optional? I don't think so. I think stack pop simply... no, that is really weird. So what is optional in here? Is that a program that is optional? No, it is a string. So it says that means this thing is none, but it is not. So you see, sometimes MyPI is not actually particularly perfect. Incompatible return type, so list of optional OPs. Okay, this is really weird. I think okay. So yeah, essentially we're pushing OP to program and it's initialized with none. Okay, I see what's going on. So, and since it doesn't know exact type, it assumed that it's some sort of a list, but then it inferred that it has to be list of optional operations. If I do something like OP, it will produce a more sane compiler error, right? So there we go. Okay, so that makes sense. That makes more sense now. All right, I'm really glad. All right, so what we're doing is that we're pushing that OP, I suppose, at the end in here, which is not ideal, I think. Which is not ideal. So what we're doing in here, we're essentially checking all of the tokens, right? We're checking all of the tokens, and at the end, this is unreachable, and within this thing, we're checking all of the keywords, right? We're checking all of the keywords. So I suppose this thing should be also unreachable, right? So assert false unreachable. Oh, by the way, I heard that people don't like that I do assert false not implemented, and instead of like rice not implemented or something. So I'm gonna keep doing that, right? And furthermore, I'm gonna actually end some of my lines with a semicolon, right? So just to make people mad. Okay, so what do we have in here? I think to advance the compiler assisted refactoring even further, I think we need to get rid of this operation, right? So we have to push things in their corresponding places. Okay, that was really weird. So that didn't help at all, right? So as you can see, MyPI is not particularly a substitution for proper static typing, because sometimes it works okay, but sometimes it's just like doesn't make any sense, I guess. Well, I mean, Python is a very dynamic language, right? So I suppose MyPI is trying to do what it can with what it has, proper English, I'm sorry. Okay, so what I want you to do in here is that I want you to, I suppose, push this thing into a program. So we're going to do append. Right, we're appending, and we're also incrementing the IP. IP stands for instruction pointer, not for internet protocol. Okay, so I need to do this thing. So this is going to be exit. So program append IP +1 program append. Don't forget the semicolon, of course. Don't forget semicolons in Python. And so another thing is a program append. Bike shed has to be read. Bike shed must be read. Okay, so that's cool. So, and also if we do OP, so this one is interesting. So if it's if, that means I need to do OP type if. but we don't have a value for that thing yet, right? So the only thing we can provide, we can say that it's going to be if operation, and the location is going to be the location of the token that we're currently handling. Token log. I wonder if I can just get rid of the OP now. Okay, I want to see if MyPI will complain. Okay, so this is perfect. This is what I wanted to see in here, right? So OP type else log token log. There we go. Do we have anything else? Type OP type and log token log. I should probably not restart it that often. Type OP type while log token log. Next one. Do token log. Next one. All right, this one is interesting. So if we see include, we want to probably use location of the token rather than the operation, because we don't have operation in here. Okay, so, and this one is also location of the token, and that one, okay, also location of the token, token, cool, all right. So is that it? That is actually really, really weird. You know why? Because we didn't modify the Lexa, right? The Lexa right now does not produce keywords at all, right? It produces integers, words, and some other shit, but it doesn't produce keywords. And I suppose this is because we don't have any assertion in here, right? So then, oh, we didn't even check those kind of assertions, right? So one thing I can try to do, I can now try to run tests and see if any assertions break. There we go. So token type, all right, that's cool. Okay, that's actually perfect. Yeah. So I put this assertion here to not forget to update the value, but I didn't forget to update the value, so I'm going to just increment this entire stuff. All right, so exhaustive keyword handling. It says that it's not 6 of them, really? So there is a 6 of them. Let me take a look at this entire thing. Am I crazy? It's 7 of them. What did I forget? Let me see what I forgot. If and... I forgot else. Okay, so you see, these kind of assertions are useful, right? So let's put else in here, in the keyword. Keyword else, and so exhaustive, and I forgot to increment this counter, of course. What do we have in here? So now we have less actual operations, right? We have way less actual operations. So we have 29 of them, so I suppose I can just do that. So I also made a note in here. Keep in mind that not all of the new ops needs to be defined in here, only those that introduce new built-in words, which is correct, I suppose, right? So if it introduces keywords, it shouldn't be defined in here. But here's the interesting thing. There's also operations like push int and push str, which and they don't have any representation in built-in words, which actually further confirms that we need to separate built-in operations into its own entity. So we introduced keywords, and now we need to also introduce built-in words, and OP type is going to be push integer, push string, or run built-in. So the amount of actual OPs is going to be actually very small, and maybe these things also could be OP. I'll need to think about that. So, but yeah, I'm going to put it to do. Extract built-in words into all built-in words into a separate OP, right? So basically consolidate all of the built-in operations like plus, minus into a single operation that is just built-in OP. Let me see what we have in here. So 29, So is it not 29? That's kind of sus, not gonna lie. This is probably because, yeah, again, yeah, this is kind of, this only further confirms that it needs to be separated. 36, all right. So let's put 36 in here. All right, next one. So exhaustive handling token types. Okay, so keyword, we actually handled keyword. I didn't forget to handle keyword, so I'm gonna put 5 in here. Unknown word include. Okay, so this is precisely what I was talking about, right? So the lexer didn't recognize this as a keyword because we don't have any assertion for that anywhere, right? So let me do lex line. And the assertion that we have to have in here is assert len keywords. Actually, token type. The amount of token types that we expected in here was 1, 2, 3, and 4. Right. Exhaustive. Handling of token types in lex file, in lex line. Right, and there we go. So it is failing, and how we're gonna actually do that, right? So we take a look at this entire thing. So I think we have to do that in the word, right? If something is about to be produced as a word, where is the word? We first need to check. Yeah, we first need to check if that word is within the keyword names. If text of token in built-in words, actually keyword names, that means we're gonna yield token type. Token type, keyword, location, actually not the text of token, but rather keyword name, text of token, like this. Otherwise, this is going to be the word. There we go. So now we're handling this entire thing, and you can say that, yeah, we're handling like 5 of them. All right, so what else do we have in here? Keyword. Exhaustive keyword handling. All right, there was like 6 of them, and yeah, there was supposed to be 7 of them. 1, 2, 3, 4, 5, 6, 7. All right, so there's 7 of them, so should be fine. Okay, expected end at the end of the definition, but got print. Oof, 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 oof. This is actually really, really oof. I wonder why did you expect and? Wonder why did you expect and? Did we not push that thing there somehow? So I need to take a look. So token word. Ah, I see. I see. So it's supposed to be token type keyword, and the value has to be not just and, but actually keyword and, right? Because now, yeah, we got rid of these specific strings. So the type has to be a keyword, and value has to be keyword and. There we go. So that makes sense. Is it okay now? All right, so here's another place. So we finally reached the simulation, right? We finally reached the simulation. So in a simulation, I suppose p type macro. So do we have a macro in here? I think we straight up removed it. Yeah, I think we straight up removed it. So I can just go ahead and change this entire thing to, what was that? Len op type 36. Okay, so let's actually say that it's going to be 36. So, all right, so we're fine with the simulation. So now we need to do the same for the compilation. Macro, okay, so there is no macro in here, so 36. Is it going to work? And it is working. So all of the tests are passing. So we refactored a thing in dynamic language. Okay, so these are just test cases. What about the, the examples, right? So examples also serve as a test cases. Okay, so they take a little bit longer time because rule 110 specifically produce like a long output and everything's fine. So we extracted keywords out of the OP type, which is kind of cool, and MyPI actually kind of helps us. So let's actually check MyPI one more time. So Porth Pi, everything's okay, and yeah, it was not perfect, it was not ideal, but it was something, right? So it kind of helped us to do this entire thing. All right, so now if I want to add a new keyword in the future, it will be quite easy to do that in here, right? So I'm gonna just do it in here, and I will follow the compilation errors and also asserts. Okay, so I introduced it to separate built-in words into their own entity as well. So maybe I'm gonna work on that too right now. We'll see. Cheers, by the way. But before I do that, I think I want to create a separate branch and just commit what we have in here. So how many changes did we do? Quite a few changes here. So, all right. So I have a macros branch. So did I forget to actually move to a different branch? I think I did. Just a second. So I have some local changes. Let me fetch the latest stuff. I think nothing is required to be fetched. Oh no! Look at that. Okay. Refactor. Let's call it refactor. And I'm going to unstash this entire thing, and let's do the following stuff. Factor out keywords out of OPs, right? Maybe I need to capitalize the keywords. There we go. And let's push that right into the repo. So, all right. So let's go ahead and introduce the built-in words, right? That will be interesting, I think. Built-in words. So let's introduce class built-in. I want to put words. It's too long. Built-ins. Let's call it built-ins. Why not? Okay. So and built-ins is these things. Right, and I think the constructions, the thing that form constructions are going to be part of the OPs anyway, right? So I'm only extracting those things that could be potentially then implemented as separate procedures or macros from the language itself, right? So things like if, else, while, do, they're like very special things that cannot be potentially implemented as procedures of the standard library. But things like dupe, swap, if we can come up with more atomic operations, with more fundamental operations, they could be. So, and that's sort of the criteria for moving things into built-in, right? It's sort of like a built-in intrinsics. This is a good word for that. Intrinsics. Is it too long? But I really like it. Yeah, let's call them intrinsics because that's what they are. Right, so in C, intrinsic is like a function, something that acts like a function, but in reality, it's not a function that is written in C. It's sort of like a compiler magic. And yeah, this is an intrinsic. Why didn't I think about that word? This is perfect. Okay, so this is an intrinsic. So, all right. And things like push int, push str, if and else, they're not intrinsics. They're like actual operations of the language. Though intrinsic also operation of the language, and we'll see how it is in a moment. So I also want to put this to do under the intrinsics. This is perfect. I didn't think I'm going to come up with such a perfect name for this thing. All right, so here are intrinsics. Maybe it's not plural, just intrinsic. And this one, OP type, could be intrinsic. Intrinsic. Do we have to put N in there? Intrinsic. Yes, you're supposed to intrinsic. Okay. Auto. There we go. So do we need to do anything else? I don't think so. That's pretty much it. And let's just try to compile this entire thing. All right, so there's a lot of errors in here, which is nice. Okay, so here we have OP type plus. So what we have to do instead in here is that if OP type intrinsic, right? And now we need to put everything that is intrinsic under the this branch, right? So let's actually quickly select everything in here. So if is not intrinsic, 1, 2, 3, 4. So if, else, and we might as well actually. You can clearly see that they are not intrinsic, right? So if each intrinsic has like a very similar implementation, and something that is not intrinsic, like a structure, they have something like convoluted thing, right? You can clearly see them. So it's yet another hint that it has to be like structured differently. So this is going to be the end, and I'm gonna put this stuff somewhere here. There we go. All right, that is cool. So print is definitely an intrinsic. Dupe, swap, drop over, but not while. While and do are not intrinsics. There we go. We're gonna put them above in here. All right. So memory, load, store, and so on and so forth, they are intrinsic as well. Syscall 1, well, this is sort of like emulation, right? So right, 1, 2, 3, 4, and this is else, assert, false, unreachable, reach the unreachable, row find the power. And in here, so this one starts with actually if, and we need to assert that length of the intrinsics, I don't know, it has to be equal to something, right? Exhaustive handling of intrinsics in simulate little endian Linux, right? It's simulating little endian machine. So I don't know what exactly has to be in here, but the execution is going to fail here anyway, so it doesn't matter. So what I need to do in here, I need to replace OPT type with OPT value, right? Not OPT, OP. I'm already tired. Okay, so let me quickly select everything in here. Query replace OP type, OP value. 1, 2, 3. I don't need to count that. So OP values. And did I update OP value in there? I don't quite remember actually. So what I need to do in here, I need to add intrinsic. Right, there we go. So we had integers, strings. So integer is needed for push integer, and string is needed for push string, and intrinsic is needed for intrinsic, believe it or not. Maybe I'm going to put it closer a little bit. And GMP is an address, and it's needed for if, and, else, while, and do. You know what's interesting is that maybe the address could be also part of the value of the operation. It's sort of like an operand, and for the address, we could have like a separate type alias and whatnot. That would be also kind of cool. So yeah, I think I'm gonna put it to do in here. Merge value and GMP. There we go. Okay, so the actual like intermediate representation of the language becomes smaller and smaller and more concise, which is nice. An intentional rhyme, by the way. So let's try to check the typing, and all right, so something went wrong. Oh yeah, I also have to replace OP type with intrinsic. Yesu, kawaii freaking desu. Replace OP type intrinsic. There we go. Boom, boom, boom. All right. Cool. What else? Okay. Oh, we're done with the simulation, and now we are in the compilation. So, and this is what we have to do yet again, but in the compilation, right? So, else if OP type is OP type intrinsic, right? Intrinsic, and let's actually put everything under intrinsic. Okay, if is not an intrinsic. 1, 2, 3, 4. So if else form blocks, right? They form special structures. I know that also below we have something like do and while, so I think I'm gonna copy paste them in advance. So here is the do and while. Right, intrinsic, and I'm gonna copy paste them here. There we go. So now I know for sure that everything until the end has to be put under that branch. Right, there we go. As you can see, this is a very idiomatic Python code. Right. 1, 2. Actually, I think it has to be something like this. 1, 2, 3, 4, and this one also has to be unreachable, right? Do we actually have like a, you know, an exception for unreachable? We do have an exception for like not implemented, but do we have something for unreachable too? I don't know. Maybe we do. Here's unreachable. Reach the unreachable. Okay, so this is the OP type, and here we assert intrinsic, right? I don't know how many of them in there, but whatever. Exhaustive, intrinsic handling in generate, right? Generate NASM function. There we go. And we need to replace OP type with OP value. OP type with OP value. Boom. Ah, it completely failed. One more time. Boom. And another thing, we need to replace OP type with intrinsic. Right? OP type intrinsic. There we go. Cool. Right, let's see. Did it fix anything? Now. Oh, this is actually cool. So these are not built-in words. They're more like intrinsic names, right? So we have keyword names, and now we have intrinsic names. Intrinsic names. There we go. Exhaustive, intrinsic names definition. Keep in mind that all of the new ops need to be. Now it's not a problem, right? So intrinsic is by definition something that has a name, so we don't even have to put the remark in here. The fact that we remove the remark means that we're going in the right path, right? So every time you need to make an exception, maybe the entire system is not really like well defined. So OP type, and there we go. So this is intrinsic names. All right, so so built-in words and intrinsic names. If the token value is in within intrinsic names, then operation. Oh, this one is interesting. So the operation type has to be OP type intrinsic, right? Intrinsic, and the actual value has to be taken from the intrinsic names, right? Intrinsic names. There we go. That's actually perfect. All right, so here's another one, and redefinition of intrinsic word. Intrinsic names, right? So if you're trying to define a macro and the name of the macro matches with an intrinsic name, it will also throw an error, right? You're trying to redefine an intrinsic word. And intrinsic definition of an intrinsic, right? Okay. And we fixed all of the compilation errors. Let's take a look at the tests, right? So MyPI definitely actually helps in here. Okay, so this is not a proper assertion. So how many of these things we have? So how many intrinsics? 29 actually. Okay. 29. So really? It would be nice if it actually printed them. You know, I have an idea. What if I do something like len op type? Ah, shit, fuck, damn. It has to be intrinsic. Okay, next one. Exhaustive OP handling. So yeah, the amount of operations we have now is actually way smaller, right? Let me see. So that's the whole amount of operations. It's like 8 of them. So now it is 8. Okay. So this one is 29, I know for a fact. Okay, so we have other things. So OP type, we do handle OP types in here. So this is 8. And then for the intrinsics, 29 intrinsics. All right, would you look at that? So we actually refactored everything correctly. So what about the examples? Do examples work fine? Hopefully they do still work fine. All right, everything seems to be working fine. So we've done a pretty big refactoring and nothing is broken. Everything is working quite well. We can even check that. So we have a pretty big example in here, which is called Rule 110. So this is an example that implements Rule 110 cellular automaton. And this is kind of like a demonstration that our language is Turing complete. So, and we did a pretty big refactoring over 1,000 lines of code of Python. And let's see if this example still works, if it still generates the Rule 110 pattern. Right, so we're going to do compilation, and after the compilation, please run this entire thing, and there we go. So this is a Rule 110 pattern. This is how it looks like. Yeah, so it still works. So this is the beauty of static typing. Static typing helps you, it guides you through the process of refactoring. In fact, it's really difficult to refactor the code without any static typing, only using dynamic typing. It's possible to do that with dynamic typing, but it's much harder, because you need to go through all of the possible execution paths. When in static typing, you don't have to go through all the possible execution paths, you just get that for free. Right, so the type checking itself automatically goes through all of the execution paths for you. So you don't even need to write any tests to do that. So this is actually beautiful. But anyway, let's do a committee. So factor out intrinsics out of, is that even a proper English? I'm not sure. Out of OP, right? And I'm gonna just push that right into the repo. And let's create a pull request and see how many changes we've made. So I think it's a pretty decent refactoring. So 510 deletions and 530 additions. So it's a pretty decent refactoring of a dynamic program. Right? There's a lot of things in here. This is a pretty complicated program, but all of the tests pass, and the static typing actually helps us to move forward. Right, so I'm gonna just do that and see if CI is still working, So look at that, So now it is a little bit easier to change things around. So I really like that. All right, and that's pretty much everything I wanted to do today. Hope this small little session, small little demonstration on how I use static typing in Python was useful. So thanks everyone for watching. Check out all of the links in the description and stuff like that. Where is the description? Here's the description. Check out the source code and whatnot. Also check out MyPI. MyPI is a pretty cool thing, so I'm going to put it in the description. And I see you all next time. Love you all. Mwah.